Hello everybody and welcome back to our third hands-on tutorial for this artificial intelligence course. The last time we looked at how we can fit a k-nearest neighbor model and how we can visualize the data we are working with. And in this hands-on we will look at how we can properly train such a model and how we can evaluate the performance of such a model. So what we do first, we create a copy of our last hands-on, or you can also download it from the Moodle website and upload it here. So I create just a copy of the last one and then I rename it. So I click here, rename, and I call it hands-on number 3, model evaluation. And now I open this Jupyter notebook. And then we see here the code from the last time. What we do first is we first run all the cells. So we execute everything again that we can do here by kernel, and that we click here restart and run all. That's restarting the kernel, it's running all the code that's in here. That we just load everything into the memory again. And then we have seen the last time that we worked here, or in the last session we worked with this data set, the breast cancer data set, where we would like to predict if a specific patient has a malignant tumor or a benign tumor. And there we had 569 samples, and we reduced it to a set of 10 features. And we also looked at the class distribution, where we found out that 212 patients have a malignant tumor and 357 have a benign one. Our goal is now to build a classifier that can predict with high precision and recall and high accuracy the status based on the features if a specific tumor is malignant or benign. And the last time we found out, when we do it quite naively, that we say here, for example, our k-nearest neighbor classifier has a neighborhood of 1, and we fit the data just as we stored it, and then we predict on the same data that we do all the predictions correctly, because it just remembered the data and it looked at the closest neighbor. And of course, if we take the same data again, the closest neighbor is already in the data set. So it will always do the predictions correctly. But that's just an artifact, and that's how we should not do it. In this lecture, we will look at different ways how we can properly evaluate such a classifier. And we also look at an example how we should not do it again. So what we do first here is we first import from the scikit-learn package as import sklearn.metrics as metrics. So we import different metrics. So it's a submodule of the scikit-learn package, the metrics module, and it already implemented some of the commonly used metrics. We also looked at the lecture. So for example, the F1 score, we can get here the confusion metrics, we can get here, for example, the recall score, the precision score, and so on. So it provides us a set of different measures. However, also not all of the measures we looked at are implemented here in this package, and therefore we can always go back to the confusion metrics, which we will get with this function here, and we can compute them ourselves. So let's go back here. We first implement here the scikit-learn metrics package, and then we import from the model selection package. That's an additional one, sklearn.model selection. From there we import the train test split method. This method already implements a convenient way to split the data into a training set and into a testing set as we like it. So let's say here our X train, X test, Y train, Y test. These are 4 variables. This is equal to train test split. So we call the method train test split, and this method returns to us 4 variables, one which stores the training data, one the testing data, and also the labels for the training data and the testing data. And what does this function would like to have? It likes to have a few arguments. Of course, it would like to have the original data X, which we like to split. It would like to have the labels, we have to set the test size. So the test size should have a ratio of 20%. So 20% of the sample should go into the testing data. And we can also set a random state. So the random state is equal to the seed, as we already looked at in NumPy. And this initializes the random number generator that we can reproduce our numbers or our splitting here. So we now split the data here, and if I execute this, we see, okay, it worked, we didn't get any errors, and now we can look at the shapes of this data. So therefore, let's print again the shape of our full data set. The shape of our full data is equal to plus str, the original data set, x.shape. And now let's look at how large the training data is. So the shape of our training data is str.x_train.shape. And the same we do for the testing data. So we just copy the line here. We replace training with testing, and here xtrain with xtest. And if we execute this, we see that the shape of the full training of the full data was 569 samples and 10 features, and now the training set only has 455 samples and the testing set has 114 samples. So 20% of the samples go now into the testing set and 455 samples into the training data. And now we can refit our classifier. So let's copy here our k-nearest neighbor classifier from above. So we now say here our k-nearest neighbor classifier, we take a neighborhood of 1 and we take here the Euclidean distance. Then we fit not on x and y, we fit now on x train and y train. So we store in our training step the training data in the k-nearest neighbor model. And the predictions now we don't do here on the full dataset X, we do the predictions on our test data. Let's call this here in the beginning predictions, the variable predictions underscore test. As a sanity check, we do the same on the training data, because we know if we fit or if we predict on the training data with a neighborhood of 1, we should get a perfect classifier. And this we just do as a sanity check, and to also prove that our model gives a different performance on the test data. And then we do here the predictions train, and predict X train, and now we can compute the performance measures. And therefore we compute the accuracy. So the accuracy on the training data is metrics dot accuracy score, and there we pass for the training data the true labels, so y train, that are the labels from our training data, the true ones, and we pass the predictions train, and the same we do for the testing data. So we just copy the line, we say here the accuracy of our test data is metrics.accuracy, now the true labels of our test set and the predictions of our test set. And now this function computes for us the accuracy of both training and the testing data. And this we can print here, so print accuracy on the training set. And this we print now with 2 digits or 2 decimal places, so %.2f, and we pass here the accuracy of the training. Then we copy the line and we replace training with test here, and then we can execute these few lines here. And you see now that our accuracy on the training data is 100%, so 1.0, which is not surprising because we test our classifier on the same data as we have trained it. So here we get a perfect classifier, which of course is an artifact. And when we look now at the test data, which is new to the classifier, it has not seen it before, it can get correct predictions with 86% probability. So 86% of our predictions in our test set are correct. That doesn't look too bad. But we could now ask ourselves, do we get better with a different neighborhood? If we take more neighbors into consideration, can we get better predictions here? This we will look at in the following, but before I also would like to give you a small exercise for yourself. So here we just computed the accuracy. You should now look at the API, here at this scikit-learn API, and you should also try to compute some of the other metrics that we have looked at in the lecture. So for example, the F1 score, the message correlation coefficient, recall, specificity, sensitivity, and so on. So that's up to you now that you implement them and try it out. So we will now continue to look at an example that we try out different k values. So let's say our neighbors is a NumPy array which starts at 1 and goes up to 51. So we would like to try out 50 different k's starting at 1 up to 50. And of course, then we would get 50 different accuracy scores for the testing and for the training data, and that we have to store in a list. So we can write here our accuracy on the training data and our accuracy on the test data. Both are lists because we will now get for every k a different accuracy measure, and on the test set and on the train set. And then we need a for loop. So for our k in our neighbors array, we do the following. And now we just copy the few lines here from above without the print commands. We paste them here. Then we mark those stuff here because they have the wrong indent, and we press the tab key, and then this we have to also shift in. And now we replace here in the k-nearest neighbor classifier the n neighbors, which is equal to 1 here. We replace the 1 with k. So in each iteration we will now learn a new classifier using a different k value and the Euclidean distance, and we will fit it on the training data, and we will make our predictions on the test data. And then we compute here our accuracies. So we just rename this as ACC train and ACC test, that we have two different names because here already we had a list and we don't like to override the list with a new name. So we rename this here, and then we append to the accuracy training list, we like to append the value from here so that we just store them in the list. And the same we do for the testing. So accuracy test is ACC test. Now we go out of the for loop and let's go through it again. So first we say we like to test 50 different values. We have two empty lists where we like to store our performance measures, and then we have a for loop that we fit 50 times different k-nearest neighbor classifiers with different k's. We train it on the training data, we test it on the test data and also on the training data to just get a sanity check here, and then we compute the accuracy score and store it in our training data. Now after we did this, we would like to know what was the best model. And the best model has of course the highest accuracy on the test data. And therefore I like to find out the k, what was the best k in our set. And that we can find out. So the best k was there where np.argmax, the highest value in our accuracy test array. So this returns the index of the highest accuracy score in our list of accuracy test values. So there we have stored 50 values. This tells me the index where the highest of this accuracy scores is stored, and then I can access in the neighbors list the index where the k value was that I used to get this model. And then I print this, so print best k is equals to str best k. And I also would like to know not only the best k, but also the highest accuracy score. So we print also the best accuracy, and we print it up to 2 digits. And then we pass here the accuracy test. I have a typo here. And I say np.max accuracy test. Then I execute this, and I'm getting an error because I have a typo, accuracy. That's I just have to, that's in line 13, so it's here, and this I just have to replace with the correct spelling, and I have an error here as well, and now it should work. And now it tells me the best k is 5 with an accuracy of 94%. So we have to ask ourselves now carefully, is this correct what we did? Or why is this bad? And therefore, let's just visualize our data again. So I write PL figure, fig size is equals to 10,6, and then we also provide a grid, and then we plot for all our k values, for all our neighbors. We plot the measures, the accuracy measures from the training, give it the label accuracy training, and we do the same for the testing. So test accuracy test, and then we plot a vertical line, AXV line, where the best k was in the color gray, and the line style of this vertical line should be dashed. Then we provide an X label, so the X label is our k, and our Y label is our accuracy score, and then we print the legend at the end. So let's execute this, and what we will get now is the following plot. In this plot we see now here at the x-axis the different k values. We tried out k values from 1 up to 50, and here you can see the accuracy. The dashed line introduces here where we found the best model that worked the best on our test data. You see in the beginning on our training data, our model has 100% accuracy. That's not surprising, as we already know from the last examples before, and then the model performance decreases here on the training data. However, here on the test data, it's getting better. And here, at this point, at k equals to 5, we found the best model on the test data. And now if we think about this more carefully, then we realize that we should not do this. Why should we not do this? In the beginning I said we have to split our data into training and testing. Otherwise we will overfit our model. And here we actually did overfitting again, because we now selected the model, the best model, so the best k on our test data. So we didn't do any internal cross-validation or internal model selection. We just trained on the training data, and then we with different k's, and then we always tested on the same test data. So we reused the test data, in this case 50 times, then we selected the one that worked the best on the test data. So what we don't know yet now is, does the model also work on data we have never seen? That we can't answer. So what we did here is not enough to select the correct k. This we can't do. We have to extend this. And in the lecture, we learned that we usually should take a training validation testing scenario, where we train, where we use the training data to fit the model. We use the validation data to select the model that works the best, for example, for different k values, and then we retrain with the best k on the full training data, so the training data plus the validation data, and test on the never touched testing data. And that's what I would like to implement now. Therefore, I copy here again this X train where we did the splitting. I copy it here. I set the random state, in this case, to 1. And then I create another copy. And now I say here I have the X subtraining, X validation, Y subtraining, and Y validation. And I do the train test split now not on the original data, but here I do it on the training data. So I take the training data and split the training data again up into a sub-training data set in a validation set. And here I take the random state. For example, let's take 4. So we have now here 20% testing, which we never touch. And the training data is again split into a sub-training data set and a validation data set. And now we can do more or less our cross-validation again. And not cross-validation, our line search again. So what we do here, we copy just this code here again from before, where we tried out the different k values and we copy them here. So we have here our neighbors again. We have our accuracy in the training, our accuracy in the testing. And now for k and the neighbors, we do again here the for loop, but in this case, we don't use the training data, we use the sub-training data. So we fit on the sub-training data and on the take also the labels from the sub-training data, and then we predict here on, we can remove the training here and we just predict on the validation. So predictions, validation, and XVal. So we don't use the testing data, we use the validation data. And then we store this data in our here accuracy test array. So our accuracy from the, this we rename in val, ACC val. This we also rename accuracy val. And then we do here on the accuracy score on our true validation labels and our predictions from the validation, and we store this, we store this here in our accuracy validation array. And then after the for loop, we again try to find the best k value, which we now did on the sub-training. And we can print this here. And now what we have to do now is we have to now refit the model using the full training, which is nothing else than the sub-training plus the validation data, using the best k value. So we write here again, I copy this here again. So k nearest neighbor classifier, and here I don't use now k, I now use the best k. And now I fit here on the full training data, which is this here above. And then I test my model on the real test data. And now we can also compute here the testing accuracy. So the test accuracy is now here of our predictions on the test set. Let's print this. So print accuracy on test is the following. So percent test accuracy. Let's execute this. And now we see, if we do it this way, our best k is equals to 11. The best accuracy from our model selection was 90. So we can also rename this in validation accuracy. Let's execute this again. So our validation accuracy is 90%. Our accuracy on the test set is 86%. So you see that we again lost some performance when we use data that we have never used before. Now, one of the questions we should ask ourselves is now, is this now better than what we did before? What could be a problem here? One problem could be that our data set is maybe too small. We only have 500 samples. We don't know if our, for example, training data, testing data, and validation data have been good splits or represented our distribution. So for example, if I remove here the random state and I execute this again here, then you see, oh, now I get a k of 5 and a validation accuracy of 89%, and on the test it got a little bit better, on the validation it got a little bit less. Now the k is different. Let's execute it again. Similar k, little bit different values here, but very similar as well. Let's execute it again. Now the k is equals to 3, 92% accuracy, so it got better. Let's execute it again. Again, k equals to 3, but here different test performance than before. Let's execute it again. K is equals to 2. Very bad accuracy on the testing, just 81%. Let's execute it again. K is 28. Again, different values. So it looks like that for every split we're doing here, if we do the splitting differently with a different random seed, we'll get different distributions of our testing and training data. And this leads to the fact that we always get different k values and different performance measures. And therefore, we should usually then use a cross-validation, because the cross-validation then creates different training and test splits and helps us this way to get an empirical evaluation of how well our model works. This splitting into 3 independent data sets is usually done in deep learning when you have a lot of data, and a lot of data, I mean hundreds, thousands to millions of samples, because then it's getting more likely that you get a real, or that you get closer to the distribution of your data set by resampling from it. So we will now also look in this last session now at how we can do cross-validation and how we can do within a cross-validation the parameter search. And therefore, I import from scikit-learn new model selection methods that should help us to do it. So sklearn model selection, from sklearn model selection, we import stratified k-fold. So what we would like to do is, in our scenario, we would like to do a stratified k-fold validation. This is what I said in the lecture, when we like to keep the ratios of the positive and the negative class. So in our case, we would like to keep the ratio of malignant and benign cancer samples. And of course, we could implement the cross-validation ourselves as well with NumPy, but this already gives us a nice function that helps us to do the splitting correctly. So our cross-validation, I call it KF, k-fold cross-validation, is equals to stratified k-fold. And now I say I would like to have 10 splits and a random state of 42. So I use again a seed that we can reproduce the same results. And then I need a few empty arrays. I need an array for the best validation accuracy scores. I need an array for the best test accuracy scores and for the best neighbors So different empty arrays, and now I create a for loop. So for train index, comma test index in kf dot split x, comma y. This is now a little bit different what we have seen before. So here we get two indices. Once we get the training indices, and here we get the testing indices for our cross-validation split of our true data and our true labels. So we pass here the full data set, and now internally, in each iteration, it gives us already the indices for the training data and the testing data, such that we can create our sub-data sets that we would like to use for the learning. So our x train is now x, and now I just pass here the training indices, training index, and x test is x test index, and the same we do for the labels. Y train is y train index, and y test is y test index. So this already creates, as I said, the different indices for the different iterations, so we don't have to worry about the splitting into this k different folds and how we do the random sampling from it. This is already done by this function for us. We just can here, using the slicing and the indexing, we can extract the data from our arrays. So now with this, we could now perform cross-validation. But we said we need some kind of nested cross-validation because we also have to optimize our model. So there are different ways of how we can do nested cross-validations. Either we can create a new stratified fold object to do an internal cross-validation, or what we also could do is we could split the training data into a sub-training data into a validation data to do the line search. And this we then can just copy from here. So we copy here this code which we implemented before, and we paste it here. And now we have to be careful that we do the indents correctly, so we have to mark it and press the tab. So now let's look at the code which we copied. So after we created here this this training and testing data sets, we now split it again now into a sub-train and into a sub-test data set. So the validation data set. And I will give it a random seed now. So I write here, comma random state equals to 42. And now we go to the next line. So in the next line we see that we have now the neighbors. So we'd like to try out 50 different Ks again. And now I compute here the accuracy for the validation. So for K in neighbors, and we pass here the K, we get here the sub-training set, we get here the validation from the before that we can do the predictions, we compute the accuracy, and we store the accuracy here in our list again. Then, after this, we select the best model, best K. We remove the prints. We don't need the prints now in the. Or let's keep the prints here. Validation accuracy, and we also write here before print iteration plus str. Okay, so that's we can use the K here also as an indicator of our iterations, because K starts at 1 and goes up to 51, so it tells me at which iteration I'm currently at. Here we get the best K, here we get the maximum accuracy from here. Then we refit our model as we did it before with the best K on the training data. Now we test it on the testing data, which we got here from the fold, and then we can compute the accuracy measure here, and then we add this accuracy measure to our list, which we defined here. So the best ACC test dot append test accuracy. Then we store the best k value, best neighbors dot append best k, and we store also the validation accuracies that we know how we performed in the validations, which is then here the NP max accuracy value. And then outside of the for loop, we can now compute how well we did on the cross validation. I will first write the code and then I'll go over the code again to explain you what we actually did. So what we first do is we had here these three lists. These are Python lists, and this Python list we now convert into NumPy arrays, because then we can use, for example, the mean or the standard deviation on these arrays. So the convert Python list into NumPy list. So we write our best neighbors list is now np.array best neighbors, just a conversion. The same we do for best SCC, the test values, and the validation values. And then we can print the average and the standard deviation for all these measures. So here we write now print average k. So what so for each fold or for each iteration in this cross validation, we might get a different k value. So we store these different k values in our array, and now I'd like to provide the mean and I like to provide the standard deviation. So I have to pass here a tuple, so I provide two more of this parentheses, and then I take the best neighbors and I compute the mean, comma, and the standard deviation. And the same I now do for the accuracy. So the accuracy on the validation is then the best accuracy, the validation, and then I copy this again and I compute it on the test data. And that's then here the mean of the test data and the standard deviation of the test data. Now let's first execute it. Now you see that we get a lot of printouts. Iteration 50, best k was 9, the validation accuracy was 89%. Iteration 50, okay, so it's computing now in this internal line search. Why is it? Okay, the k value is there's a small typo now. I can't, of course, not use the k here. I have to use a new counter. So I say for I, comma in. No, I have to go up here. I have to define here a counter. Counter equals to 0. And now I use the counter here to say in which iteration I'm at. So iteration counter, and then I increase here at the end the counter by 1. Plus equals 1. Now let's execute it again. Now you see iteration 0, we had the best k was 9 and the accuracy of 89%. In iteration 1, so in the next iteration, the best k was 5 and we had an accuracy of 90%. In the second iteration, k was equals to 8. So you see that k values are different for each fold, and then you get the validation accuracies. And here at the end, we get the average k. So the average k was around 40 with a standard deviation 14 with a standard deviation of 5.5, and the validation accuracy was around 92% with a standard deviation of 2%. And on the test data in the end, so we had now 10 different test data because we did a k for cross validation. We now get 89% with a standard deviation of 4%. So this is exactly in line with each other. So we built now a model that is very good in predicting on unseen data, and we empirically evaluated this, and with the standard deviations we can see that both are more or less in a similar range. So now we can say that we can predict if a specific tumor is malignant or benign for this breast cancer data set with 89% accuracy. So let's look at this code again, what we actually did. So I said in a K4 cross validation, for example, when we have 10, we create 10 different training sets and testing sets. So we resample, so we split the data into 10 equal folds. Then we take 9 for training and 1 for testing. Then we take the other set of 9 folds for training, and we use this other one for testing. So more or less, all the data has been tested once, but we never use the testing data to train on in the same iteration. And this we can do here. So here we get the indices for the training data and the testing data for all our 10 different splits. And then here we do this internal line search. So that's the internal line search to fit or to find the optimal hyperparameter K. So here we split the training data again into a sub-training data set and a validation data set. Then we try out on this validation set 10 different K-values. So we train on the sub-train and we test on this X-val. Then we take the best performing model, retrain here on the full training data, make the predictions on our test data that we have never used here to find the optimal K-value, and then we store the values in our internal data structures that we then in the end can compute here the average K, the accuracy on the validation data and the accuracy on the test data, and then we see that or how well our model works. And we can comment this here out, this internal printouts, then we only get the final result. So here accuracy of 92% and a testing accuracy of 89%. And now we can also try out if we remove here the random states, if the results are more or less stable. So we execute this again. And then you see that you get quite similar values here. So the K is quite different. So it has a different mean, but here the validation and the testing accuracies are approximately in line with before. So we can execute this now again. And here it's now a little bit different, of course, but it's all, as you can see with the standard deviation, all in the same range. So all the results are more or less comparable. That brings me to the end of this tutorial and this hands-on. I prepared some exercises for you that you can try out the things yourself again, that you can create this training and test splits, that you implement your own cross-validation, but also that you more or less also create all the other metrics, because now we only work with the accuracy, and I said only looking at the accuracy is not good. So we also have to consider the other values like the precision and the recall, the true negative rate, and so on. So this you will try out in the exercise yourself. That brings me to the end. I say thanks, and I see you at the question hour.